Okay, I'm going to be solving another moment of inertia tensor problem, this time with a cube from the 2021 classical mechanics subject exam. Okay, so the first thing we have to do is compute the volume integral of the density to validate that it yields the total mass of the cube.
Okay. Yeah. So I guess the moral of this.
So
I don't understand because the files.
M should be equal to the mass density integrated over the entire volume. And that is equal to triple integral overall space, so 0 to negative infinity to infinity. And the heaviside step functions are going to set the limits of this integral, these three integrals. So if this here means that the volume is only finite when the absolute value of x is between is less than a over 2. So these limits are going to be, so there's a constant m over a cubed, and then all these integrals will have limits from negative a over 2 to a over 2.
For all times. But the problem was that in order to
and none of these integrals depend on x, y, or z, so they're all the same. So I'll just do one of them, the integral over x from negative a over 2 over a over 2 is a over 2 minus negative a over 2. And we have that same integral 3 times. Well, this is just a, so we get m over a cubed times a cubed just gives you back m, which is exactly what the problem wants us to do. And okay, no, number 2, we have to solve for the moment of inertia tensor again. So
you can see that this effective wedge setting has a little bit more production for these two isotopes. But I guess so I mean they're about relatively the same. So I would say this thing is pretty good. This is the reduced yield plot I got from this setting here.
so technically, and okay, so the individual components of the matrix are again given by this formula, the volume integral over r squared times delta function minus rj over the entire volume. So technically this is 9 integrals again, but we know that because the tensor is symmetric, that iy is equal to xy is equal to yx, and xz is equal to zx, and zy is equal to yz. So we really only have to do this one, this one, this one of these two, one of these two, and one of these two. So it's really only 6 integrals that we have to do. And so let's start it. So xx, the delta function is 1, and we have an x squared here, so it's going to be the integral over r squared minus x squared, which is y squared plus z squared.
I was seeing an agreement between the two.
So then there's the constant out front, and then we have 3 integrals, again with the same limits of integration from the heaviside function.
So we use, okay, and I next try comparisons.
dx dy dz. And the first integral has no x in it, so that just pulls out a factor of a. So we get an a from the first integral, and now we have to do the other two
And
integrals,
I
which
just want to show a very sad bug that happened to me. My entire log normal iter lived by itself. So basically, as I was running it, it crashed and it corrupted the file, so it actually cannot.
the first one,
So
the y integral
it's
is going to give you y cubed over 3 plus z squared y
I don't know.
from
I guess it's just
a over 2 to negative a over 2. And then there's still the outer integral after that we have to
It
do.
does stuff like this.
So if we look at just at this inner part, that is 1/3 a cubed over 8 plus z squared a over 2 minus 1/3 negative a over 2
It is not possible. Sorry. So,
negative
but I have a backup.
a cubed over 8
We have the same age data for
plus z
types of
squared.
things, so I'm like that. But it's already, and I'm also doing.
And if you pull out the negative sign, it's just gonna be the same thing twice. So it's equal to a cubed over
Approximated, that's like
24 plus z squared a over 2 plus
And I'm also going to. And then essentially what it will do.
plus another
all
a
of these
cubed
type of
over
like
24
beams
plus
from their models
z
together and
squared a over 2, which is equal
I'm
to
also looking into how to
a cubed over 12 plus z squared a.
So, and yeah.
So that was that inner bit there. Now we still have to do the outer integral. Where xx is equal to
So don't worry about this.
factors canceled out there. So we're left with a squared times the integral
Oh, yeah.
this time
Yeah.
integrating over z. There's no z dependence left on the first term, so I'll just give another factor of a. It's gonna be a to the 4th over 12 plus z cubed over 3 that's a cubed over 8 minus negative a cubed over 8. Is going to give 1 over 8 plus 1 over 8 is 1 over 4 times 3 is going to give a to the 4th over 12. Cancel out these here. 1/12 plus 1/12 is 1/6. So this is equal to 1/6 m times a squared is equal to ixx. And now the other diagonal components I, y, y, and I, z, z are actually these, it's the same 3 integrals, but just in a different order. So I, y, y is equal to m of a cubed Right, one more intermediate step. Iyy is now the so if we look back at the formula, y gives you 1 from the delta function, so it's r squared minus y squared. So that's x squared plus z squared now instead of whatever it was before. Integrate over the entire volume again. And you can do these three integrals again if you want to, but if you work it out, it's going to be the exact same three integrals as ixx, just with a change of variable or just changing the order that you do these integrals in. So iyy is equal to 1/6 a squared, just like ixx, and so is izz. So all the diagonal elements are the same. Now we have to solve um, off diagonal elements. So and remember that so I y x is equal to I x y. And let's go back up to the formula. This time I is not equal to j, so we don't have the r squared. So we just have negative xy to integrate over. So negative xy over the entire volume is equal to negative sign out front. And actually, we only have to do one of these integrals as well, because if you just take the inner integral, for example, you're going to get x squared over 2 integrated from a over 2 to minus a over 2. Well, when you square the negative sign, you're going to get the same. So it's 1/2 a squared over 4 minus the negative is squared, so it's a squared minus a squared, which is equal to 0. And if the inner integral is 0, all three, the entire thing is equal to 0, and the other one is equal to 0. So we have a bunch of things that are equal to 0. Iy x is equal to 0, which means ixy is equal to 0. And all the other off diagonal elements are going to have a very similar story, because it's always the integral over one of the coordinates just to the power 1. I can do one more. So the next one we need, for example, would be izx. That would be the integral over negative zx. Got the density there, but it doesn't matter because it's 0. So here, if you do the integral over x again, you get the same thing. So all the off diagonal elements are going to be equal to 0. So now we can write the complete moment of inertia tensor. One thing I forgot to mention in this first part of the problem, we're doing the moment of inertia tensor with respect to the center of mass. And we were doing that already because this cubed was centered at the center of mass, and the origin of our coordinate system is the center of mass as well. So I forgot to mention that at the beginning, but the moment of inertia tensor that we're solving for right now is with respect to the center of mass. So I'm gonna write, because that's gonna be important for the next part. Here, I'm just gonna write the moment of inertia tensor with a subscript center of mass like that. And six. So that's the answer to part 2 of the problem. Now we need to find the moment of inertia tensor with respect to the point in the bottom of the cube, the front lower left corner indicated by point P, and compute the moment of inertia tensor through that point. So the way we're going to do that is we're going to use the parallel axis theorem again. So if I just draw this cube with origin was something like that. There's the cube, and the point that we're finding the tensor around now is there in the lower left hand corner at negative a over 2, negative a over 2, negative a over 2. And the angular momentum is going diagonally through the cubed like that with just the vector 1, 1, 1 diagonally through the cube. That will be important later. But for now, we're going to use this second formula for the moment of inertia tensor, which shifts the moment of inertia tensor by a vector that is parallel to the center of mass. So we have all these components from the center of mass. Where capital R is the distance from the origin to this point. So it's just the same as so the first thing we need is to find the magnitude of the vector, so squared. So we'll just take all the components and square them. So we get a squared over 4 plus a squared over 4 plus a squared over 4 is equal to 3a squared over 4. And we can update this formula. Plus m 3a squared over 4 times the delta function minus r I r j. And we already know a lot. Well, only the diagonal elements of the moment of inertia tensor around the center of mass are non-zero. And if we don't have a diagonal element, this part will give us 0. And we would only be left with the Ri, Rj. And if we do have a diagonal element, all the diagonal elements are the same, and we're going to be adding the same constant to all the diagonal elements. And because this vector has all three components the same, we're going to be adding the same constant to the non-diagonal elements. So I'm going to write one of these values. So you see what I mean? So the center Ixx in the center of mass is 1/6 ma squared plus the delta function hits because x is equal to x, so we get plus m3a4 minus negative a over 2 times negative a over 2. So 3/4 minus 1/4 is 2/4, which is the same as 1/2. Adding fractions can be very hard. Okay, so that is Ixx of the moment of inertia tensor through the point P. And if we were to compute Iyy now, it would be the exact same thing because we would get the delta function hit, and this part of the tensor would look exactly the same because y, x, y, and z of the vector are the same. So, and same with I, z, z. And then all we have to do is solve for one of the off-diagonal elements. So let's just do x, y. That would be equal to I, x, y from the center of mass plus m. And now this first part is going to give us 0 because the delta function is not going to hit. And then we're just left with minus negative a over 2 times negative a over 2. And the off-diagonal elements from the center of mass was 0. So we get 0 plus m minus a squared divided by 4 is negative ma squared over 4. So now we can write the entire moment of inertia tensor through the point P. That is going to be equal to this guy along all the diagonal elements and this guy and all the non-diagonal elements. So 2m three. So that is the moment of inertia tensor through the point P. it's a lot messier than through the center of mass because the center of mass is no longer at the origin, so the we have all these other terms in it. So now the last part is to find is to now find the total, compute the angular momentum and the rotational energy if the entire cube is rotating through axis going through the diagonal. So we already know what the angular velocity vector is. Just rewrite them down here. And we know that the angular momentum is just equal to the moment of inertia tensor times the, well, it's not times, it's matrix multiplication, but you can write it this way. So we have to multiply the moment of inertia tensor times this vector to find what the angular momentum is. It's a vector too. So I like putting a line above matrices sometimes because so I'm gonna pull out all of the factors here. So this is m times a squared times 2/3 minus 1/4 minus 1/4 minus 1/4 2/3 minus 1/4 minus 1/4 minus 1/4 2/3 times the angular velocity vector is omega 0, 1, and 1. Now we just have to do matrix multiplication. Need another page here. Probably soon. So this is omega m(a) squared and so this basically adding these terms up here. Minus 1/4. It's going to be the same for and now we have to add more fractions together, which can be the hardest part of all this. And I'm running out of the Zoom phone, so I might have to make another part 2 to this video unless I have 10 minutes, which means I can finish it actually in this. As long as I can add these fractions together fast enough. 2/3 minus 2/4. That's 8/12 minus 6/12 is 1. No. 2/12, which is 1/6. So we have 1/6 omega m(a) squared, and I pulled that 1/6 out of them. So we have just 1, 1, 1 like this. And now the formula for last part is compute the rotational energy. Okay. So the rotational energy to rotational is equal to 1/2 times the angular velocity times the tensor times the velocity again. But this part here we just found is equal to the angular momentum. So all we have to do for this last part is multiply this angular velocity times the angular momentum, which we just found in the last. So we have 2 times 6 is 12, so I have 12 omega squared and a squared. And then this is just these two vectors dotted into each other, which is just 1 plus 1 plus 1, also known as 3, which will cancel out with this 12 to give us 1/4 omega squared a squared, which is the final answer. Okay, I hope that was useful. Thank you very much for watching.